I see. Well, let's get into atomic structure a little bit. Um, okay, this is hung again. Sorry. Let's get into atomic structure again. Now, if your electronic shell is the entire stadium and you zoom into it, you see a footballer, the ball. You zoom in more, you see the grass. Down there, a little pin. That's how big the atomic nucleus is. This is 100,000 times smaller than the shell, than the large stadium, right? So if you think about it, there really is nothing inside an atom, right? It's mostly just this fuzzy electron cloud kind of going around. And the actual nucleus, the much of the mass of the atom is a super, super tiny thing. Yeah, that's ridiculous, right? So the answer, of course, is a pinhead. But what about the electrons, right? We know that they have something to do with electricity. If you supply some electricity to them, you can get electric currents, or you can get some light out of it. So what's going on with these electrons, right? Now you zoom in, what it turns out that the electrons are actually sitting inside a kind of a ladder-like structure. Each rung of this ladder corresponds to an energy level. Okay. Electrons like to sit at the very bottom of this ladder, occupy the sort of lowest energy states, yeah, when they are just resting in a sense. If you supply some energy to them, then it excites the electron to a higher energy level on your ladder, and then it stays there for a little while, but it really does not like being in these excited states. So after some time, it would decay back. And as it decays back, it emits a light, right? When I say a light, it means a particle of light, so a photon, right? So, and the catch here is that every element, so the atoms of different elements have their own little ladders, completely distinct from each other inside them. And the spacing between these different levels of these ladders can be different. The sort of structure of the ladder can be different. You can have very rich internal structure of these ladders, right? This is why atoms of different elements glow differently. They have a characteristic different energy differences between them, which corresponds to the color of light that you see from them. And you can also see this if you go outside and look at the different headlights of cars, right? Some of them have yellow headlamps, some of them have white headlamps. Turns out the yellow ones actually use something called halogen lamps, a certain class of elements, while the white ones typically use xenon-based lamps. And therefore, these different energy levels in these corresponding elements lead to different colors of light that you see. Good. So we understand fairly well now what's inside an atom. The final thing we want to discuss is, well, how fast do atoms move? How do they move at all, right? Like, okay, we've learned that they are like billiard balls. So if you just take the atoms in the air around us, they have some motion, yeah? How is this motion? Is it really fast? Is it like a car, like an airplane? Do they move at all? Am I just completely making this up, or is it like a pedestrian? Okay. Now, everybody is confident at this point how it works? Are people just shy? Is that why they don't answer, or is there some technical glitch? I wonder.
I think they're not
Right.
used to it. That's it.
Yeah. I'm taunting them to just motivate.
You can answer in the chat also, people, if you like.
Yeah. If this is a little bit annoying to access them. Anyway, okay. Now, so it turns out that in air, atoms move very fast. Huh? So this is like in this billiard ball picture, they're sort of going rapidly around now, and they're sort of colliding with the walls of your container and colliding with each other, and this sort of random motion. Yeah, this you're familiar with, right? But how fast in reality? Okay, so I suppose some people have heard about the kinetic gas theory, and for them this is going to be much easier to believe. For those who are not familiar with this, here's a sort of heuristic picture. Temperature is essentially just the average kinetic energy of your system. Okay. Now, kinetic energy, is related somehow to the speed of things, right? So the average speed in my cloud of atoms somehow directly corresponds to a well-defined temperature. Yeah. So I can draw a temperature scale. Yeah. This is in kelvins. So 0 Kelvin is the absolute lowest temperature, a theoretical limit that is not achievable, but you can conceive of. Okay. At this point, everything has 0 kilometer per hour speed. At room temperature, 300 Kelvin, 27 degrees Celsius, atoms have a speed of about 1200 kilometers per hour. This is as fast as an airplane, indeed. Yeah. So this is really, really fast, right? So the answer to our question was an airplane. Now, the problem is that my colleagues and I in our lab, we like to work with these atoms. We want to hold an individual atom in its place, okay, catch it, look at it for some time, maybe talk to it with photons, with light, or manipulate it and study it. But if it's going at the speed of an airplane, it's too fast before we can catch it. That makes us really sad. So the question is, how do you make them slower? Well, of course, you can make them colder, right? How do we make them cold? Maybe we use a fancy fridge. We use something with liquid nitrogen in it, which can be 77 Kelvin cold. At this point, they already have the speed of a car, but that's still too fast for us. You can go even fancier with your refrigeration and use these helium-based dilution refrigerators, which can go down to a millikelvin, which feels very, very cold, right? A millikelvin is already basically 273 degrees, minus 273 degrees Celsius. So that's really cold. But even then, stuff is really fast, still walking about at human pace. So what do we do? And the catch is that you can use lasers in a very weird and cool way to slow them down to these ridiculously ultra cold temperatures where they are literally as slow as a snail, and then we can start catching them and working with them, right? But what am I talking about, right? How does this make sense? You think of lasers as these very powerful things that you can use to cut metal. You can use it to cut objects. If you put your hand in front of a laser, it can burn through it if it's a powerful one, right? So how are we going to use this to cool something down? And that we are going to come to in the next section of my talk, right? So for now, we have a little intermission, and you can ask me some questions if you have any, um, and then we're going to move forward. Okay. Yeah, Karthik, please go ahead.
Thank you, sir. Sir, actually, as you have compared the nucleus of an atom with the grass and the shell of the atom as the whole football field. Sir,
Yeah.
once my physics teacher said, like, if you want to make atom bomb, just take out the proton or maybe I think the neutron from the nucleus of the atom. So, sir, I just wanted to know the reason behind this, what he has said. So, because nucleus is much comparatively much smaller, as you have just said. So I just wanted to know the reason why taking out proton creates this much uh, uh, danger type bombs. Like I hope that you understood my question.
Okay. So now, okay, the answer to your question is a little bit nuanced, okay, and we haven't covered any of that. That basically comes in the territory of nuclear physics. But just to give you a teaser for what this is about, is that you have heard about Einstein's sort of energy mass equivalence, right? So you can convert mass into energy. Now, it turns out that a lot of energy inside a nucleus is stored in the interactions between the nucleons. Okay, so the protons and the neutrons interacting with each other that actually glues them together. This interaction holds a lot of energy. A lot of the mass of a nucleus that you measure actually is coming from the energy contained within these interactions. When you break apart a nucleus and you separate maybe some of the nucleons from it, you are producing a new nucleus. The interactions of this nucleus is different. Okay. And now you have basically an energy deficit that needs to go somewhere in this new nucleus versus your older nucleus. A lot of this energy is radiated in the form of gamma rays, maybe different particles like beta particles, and so on. That radiated energy that has escaped this new nucleus to be formed compared to the other nucleus, which had a very different energy than it, is exactly what nuclear physics, sort of nuclear energy, goes into, right? So that is what nuclear power plants are essentially trying to harness.
Thank you so much, sir.
Now, are there any other questions? Okay, if not, then we can continue. Right. So now I think you've graduated school, and we are gonna change gears a little bit, and we're going to do things at a pace that maybe things are done at a university. Yes. Um, right. So we're gonna learn something about AMO physics, this field of physics that I belong to, right? It stands for atomic and molecular and optical physics. Right? At its very core, we want to study textbook problems of quantum mechanics. And for this, whatever quantum mechanics means, yeah, we will talk about this in a bit. But we want to study sort of textbook problems. For this, we need a system that really we can play with, where we can manipulate individual particles, where we need control over all the degrees of freedom and use it as a building block to construct more complicated systems. So we can sort of have a control on the complexity of what we are dealing with. Yeah, that helps you understand things. So what we really mean by this is that we need control at the level of single particles. Now, the problem with that is that Schrodinger said at some point, one may say that one does not simply realize experiments with single particles more than one raises ichthyosaurs, dinosaurs in the zoo. Okay. Now, this is in 1952. Uh, sorry, do you want to mute yourself? I think somebody's on mute. Yeah. Thank you. Anyway, so now, well, this was in 1952. I don't know what the progress with dinosaurs is, but I want to tell you that in AMO physics, not only can we very much work with individual particles, we can bring them down to their basic quantum nature and then systematically construct many body systems to study phenomena that emerges from all of these things coming together. Yeah. And here's a little teaser for what's to come ahead. This is a single strontium ion held in place using electric fields. Okay. And you can look at this with your naked eye. This image was taken with a random phone camera or so. Okay. So let's study our system a little bit clearly. Let's establish what are the properties of our system. Now we are working with a dilute gas of atoms or molecules in an evacuated chamber. So inside this chamber, there is no air. There is complete vacuum like outer space. And the only particles in there are the particles that we want to study. From a statistical physics perspective, you can think that the individual particles are completely uncorrelated from each other, right? And these things right now look like billiard balls are free to move about. So they have some translational motion. At least so far, it's very much classical. And maybe this is a bit mundane right now, but it's going to become important in a minute, right? These billiard balls can occasionally collide. Yeah? In addition, every particle has this very rich internal structure, a ladder of states that we talked about, where the electrons can go. Those of you who are familiar with the hydrogen atom, think about the principal quantum numbers, right? The fine structure levels that you get from orbital angular momentum, or the hyperfine levels that you get from nuclear angular momentum, right? From nuclear spin couplings, right? So you've got this internal, very rich structure. And the most important thing is that internal structure can talk to light. It can talk to photons. We can manipulate where an electron sits in this ladder by making it talk to a photon. This is exactly what you see in atomic spectra, right? Every atom has a characteristic frequency of light that it likes talking to. So for a certain atom, there may be these set of frequencies. For a different atom, there are different frequencies that you use to talk to it, right? And it will respond to it if you use these frequencies. In our lab, a typical experiment looks sort of like this. We have an oven where we make our atoms. So you put like a block of metal sort of in this oven, heat it up, and then on the surface of the metal, some of the atoms get evaporated, and these evaporated atoms then go on to fill this chamber. Inside the chamber, like I said earlier, you have very good vacuum. This is called ultra hard vacuum. This is on the same order of outer space. Okay, so there is no air in there, just our interesting atoms. right? And then you can have some viewports on it to maybe look into it, put up a camera here, or shine some lasers and so on. Yeah. But there is still one problem with the atoms inside our chambers right now, in that we made them in an oven, so they're very hot, right? They're about 1,000 Kelvin hot, which means they're going about at speeds even greater than the speed of sound. What do you do at that point? And we can sort of put things a little bit more concretely about what we discussed is a problem with hot stuff earlier, right? Like one of the things that happens with hot stuff is you suffer these so-called Doppler shifts. Now, Doppler shifts is the same phenomena as when you hear an ambulance or an F1 car approach you, you hear the pitch a little bit higher. As it goes away from you, the pitch feels a little bit lower, right? So the apparent frequency of a wave to an observer changes when if the source is approaching you or going away from you. These are Doppler shifts, right? Now, that means that if our atom had a characteristic frequency or energy of light that it liked talking to, and it's a very narrow range of energy that it talks to, it broadens as a result of all of these atoms having random velocities in my cloud, right? So they have a range of velocities in the cloud, and all of these velocities sort of contribute differently to a shift, and you end up having these broadened spectral lines. This makes spectroscopy very difficult, right? So in general, a lot of measurements very difficult. The other thing is that these things collide so much that it destroys any carefully prepared internal state of the atom. So I might have prepared my atom in a certain level of the ladder where I want it to stay, but if it collides inelastically, it it destroys the state. In a quantum language, we call this decoherence. In general, this hot stuff is very hard to control and manipulate. And it's even very hard to trap. Whenever you try to trap it in a container, it always has enough energy to sort of jump out of it, right? The solution, of course, is to go colder, because once you go colder, then you get rid of the Doppler shifts and everything, and you can do much more precise spectroscopy, which is cool for fundamental physics. Once you go colder, you can also trap these things because now they don't have any energy to spill out of your container. And this is where things get really nice, okay, really interesting. This is sort of where quantum mechanics begins to start. In that, we have been talking about a billiard ball picture of atoms, right? But this is an approximation. In reality, matter is described by tiny wave packets. So it's like each particle is actually kind of a wave, right? And the characteristic length scale of this wave is given by the de Broglie wavelength, right, which scales inversely with the temperature. So at room temperature, these waves are so tiny that it's completely irrelevant at this point, right? And therefore, you can effectively just talk about little billiard balls. But when you go colder, to let's say a few hundred nanokelvins, these wavelengths become much larger. Same, they become as large as the interparticle distance between these particles. And at this point, it's important to talk about the wave picture. This wave picture becoming sort of important is exactly what we mean by things becoming quantum and quantum mechanics becoming relevant in the study of these things. Okay. At this point, you can truly call it a matter wave, right? So we want to go colder to unlock all of these things. Now, how do we do that, right? I told you I'm going to show you how to do this with lasers. Right? The core idea in this is that a laser is just a source of monochromatic light, source of coherent monochromatic light. Coherent doesn't matter right now. It's a source of light, okay? So it can shoot photons at your particle, and photons carry momentum. What we want to do is we want to transfer the momentum of the photon to the atom. Okay, let's say your atom is traveling against the light field, so it has momentum along the left direction, and your photon is sort of going in the opposite direction, and you want to transfer the momentum from the photon to the atom. How do you do this? Well, your atom had internal states, right? It had these sort of ladder like states that we talked about, and now we can just focus on two rungs of the ladder and forget about the rest. When it's in the ground state, if you tune the frequency or the energy of your laser very carefully to be in resonance with the energy difference between these ladder states, then you force the atom to absorb the photon and go into the excited state. This transfers the momentum of the photon into the atom because the total system has to have a conserved momentum, right? This amounts to a little kick that the atom gets, sort of, we call it a photon recoil. It gets a little kick in the opposite direction of motion, slowing it down a little bit. But it's in the excited state right now. It has just absorbed a photon. At some point, it needs to come back down to the ground state and give away this photon. That can happen via two ways. One pathway for that is stimulated emission, right? In this, the atom sees one of the other photons from your laser field and emits an exactly identical photon, just the same thing. Now, this photon has the same direction and momentum as the laser photon, which means it also goes in this direction towards the right side, which means that the photon recoil that you got originally from the absorption was cancelled out exactly, and there was net no momentum transfer. This is useless for what we are talking about, right? We don't need this pathway. What we need is a second method that it can decay, and that is called spontaneous emission. In this, the atom at some point just randomly emits a photon somewhere. And this is just a randomly emitted photon. There is no directional dependence, it's just spherically symmetric. Okay. So at this point, it absorbed a photon in the absorption process, got a recoil against its direction of motion. But when it emitted the photon, it got a random recoil. And the key is to do this thousands of times, where the symmetrically distributed recoils average to zero, and the only net momentum transfer you get is in the direction of travel. Yeah. So you're doing this sort of optical cycle thousands of times where your atom goes into the excited state, comes back down, goes up into the excited state again, comes back down again. Okay. And these thousands of optical cycles then just give you a net momentum change, slowing down your particle, right? But in an ensemble, in a real ensemble of gas, atoms have velocity in every direction. So how do we slow down all of these random directions? Let's just limit ourselves to the one-dimensional case right now for simplicity. Yeah? So imagine there are two directions now of motion, right? And you shine lasers from both sides, therefore. What you want to do is engineer the laser such that it only talks, this laser will only talk to this atom because it's counter-propagating, and I want this laser to only talk to this atom. Okay. What's useful now are Doppler shifts, right? Because if this atom has a motion in this direction, it's going to see blue shifted light. Okay. So light shifted to a higher frequency from this laser. Then to bring the laser into resonance with the atom, I would have to compensate this oppositely and red detune my laser, reduce the frequency. When I do that, it only is resonant to this atom, and it's even more far of resonant to this atom. Okay. And therefore, each laser only talks to atoms which are counterpropagating to it. Right. And you can plot the force due to each of these lasers on the whole atom cloud. And it turns out that one of these lasers can only exert this positive force. The other laser can only exert a force in the negative direction. Only when you add that up do you get this nice curve, which, if you focus here around smaller velocities, corresponds to just a linear drag. Now, think about the friction force that you've learned in your school classes, right? How do you model the frictional force experienced by a particle moving through a viscous fluid like water or glycerine or oil or whatever? You always model this with a linear frictional drag, right? This is exactly what this force is doing to your atoms. It's as if they are in a fluid of photons experiencing a kind of friction from them, which slows it down. And if you want to just extend this technique into all directions because they have random velocities, then you just add lasers along each axis, and thereby you get like a sort of three-dimensionally cooled sample of atoms. Yeah. With this technique, you can reach the temperatures of a few hundred microkelvin. Okay, now that's already very cold, but we can go even colder. Okay. And these techniques now go a little bit more complicated, so we don't have the time to get into the exact mechanisms of it. But in a sense, what we do is we engineer a light field where the atom has to travel across a hill and a valley and a hill and a valley and a hill and a valley. Okay. So the atom climbs the hill, and when it reaches the top of the hill, we transfer it back down to the valley sort of magically. We'll use light for it, but I talk about it in a second. And then it has to climb the hill again. Okay. So as it's climbing the hill, it has to lose its kinetic energy and gain potential energy in the process, right? while climbing the hill. So it has so much potential energy at the top of the hill. This potential energy is then carried away by a photon and pushes the atom down into the valley. And then it has to climb another hill, lose even more kinetic energy, and then that potential energy is carried away again by a photon. Okay, so it's like your atom has to kind of infinitely climb a hill, right? If you think about it, it's almost like the myth of the Greek mythological figure Sisyphus, right, who was condemned to roll this rock up a mountain sort of infinitely. Yeah? This is a very powerful technique, and you can reach speeds corresponding to the momentum contained in a single photon. This corresponds to 1 microkelvin level temperatures. Okay, this is very, very cool, and it earned a Nobel Prize in 1997 to Stephen Chu, Claude Cohen-Tanucci, and William D. Phillips for observing this and explaining the mechanism behind it. And if you're still not happy with the temperatures you reach, you can just blow on your atoms and make them cold with evaporation, right? I'm not kidding, for real, right? You're very familiar with this from everyday experiences. If you just take your cup of coffee and it's too hot, what do? You blow on it and then it gets colder, right? What's happening there? You're just evaporating the more energetic particles and then the bulk gets colder. The same is true in earthen pots, in these matkas, right? You've got water in them on a hot summer day, and these earthen pots are very porous. So some of the water evaporates from their surface, right? And this water evaporating needs some latent heat. Where does it get the latent heat from? It steals some of it from the bulk water inside the matka, taking away this heat from them, evaporating itself, but the bulk water cools down in the process. Yeah. For those of you who have studied Boltzmann distributions, you can look at it this way. I'm in my Boltzmann distribution, I have a tail of high energy particles, right? I can cut away this tail of high energy particles, which is effectively what I'm doing by evaporating some of them. I'm just cutting away the high energy particles, just sort of removing them from the system. But now my system is no longer a Boltzmann distribution. And the one thing about thermal systems is that they always like to re-equilibrate towards another Boltzmann distribution. So my non-Boltzmann distribution that I've created is going to equilibrate towards the second one, which is dotted here, a Boltzmann distribution centered at a lower temperature, right? This is how the cooling process goes in an evaporative cooling system. This is exactly what we do. We have our atoms in a container, and the highest energy atoms are going to be sort of bubbling with energy at the very brim of the container. And you just lower the walls of your container, and these high energy particles sort of spill out, they evaporate, causing the particles that are still left in the trap to become even colder and colder. This is a very powerful technique that you can reach microkelvin temperatures with. Nanokelvin temperatures with. Right now, at this point, I want to zoom out, and see how cold really is ultra cold. Right, there's a huge scales of temperatures that we've talked about. So here's a logarithmic temperature axis. All the cold stuff is on the right, and all the hot stuff is on the left. Yeah, this room is somewhere here on the hotter end at 300 Kelvin. All of your high energy astrophysical phenomena happen on this end, right? You've got your sun's surface at a few thousand Kelvin, core at a million Kelvin. Some of the highest energy phenomena in the universe, supernovae, they happen at billions of kelvins, right? Turns out that the highest temperature that humanity has ever managed to reach was this whopping 5 trillion, I think, 5 trillion Kelvin in CERN. This temperature was reached while creating quark-gluon plasmas. Okay, at this point, your particles are basically the speed of light. They're incredibly energetic. Now, somewhere on the other end of the spectrum is where all of your low temperature solid state physics happens, right? This is where liquid nitrogen temperatures are, helium, superfluid helium at 2 Kelvin. The outer space is at this temperature, right? These fancy dilution refrigerators that you see in all these pictures of IBM quantum computers, they rely here in the millikelvin regime, right? So these pictures of quantum computers that you see from IBM, this thing is actually not the quantum computer. This thing is actually the refrigerator that they need to reach these temperatures. The computer itself is a tiny chip that sits somewhere under this thing. Okay. Where this stops is where ultra cold atomic physics starts. Yeah? With Doppler cooling, this scattering process that I talked to you about, laser cooling, reaches these temperatures here in the hundreds of microkelvins. With the Sisyphus methods, where you climb hills with your atoms, you can reach temperatures down to a microkelvin. Evaporative cooling is when you start reaching these very, very cold temperatures in the truly ultra cold regime, right? Nanokelvin temperatures. When you're this cold, things start to get really weird. Okay. So we started with our billiard ball picture of a billiard ball sort of flying about randomly in this container. As we cool down, we said that they turn into matter waves and they start behaving more like little wave packets going around and have a characteristic wavelength associated to them. They also have a characteristic interparticle distance between them, right? If you go even colder, the waves become larger and start to overlap a little bit. At this point, it's very difficult to talk about individual atoms separately because they all kind of overlap. They're just like these waves with some probability of being everywhere, and it's kind of a mush, and you can't talk about it sensibly. Beyond this, when you go very, very cold, ultra cold, the whole system, all the matter waves in it overlap completely, forming this one giant matter wave, which is basically behaving like a single entity at this point. And this entity is called a pure Bose-Einstein condensate. Okay, Satyendranath Bose and Albert Einstein conceptualized this theoretically a long time ago, but it took until 1995 to actually create this one experimentally, right? This is a macroscopic quantum object. You can look at this thing, a cloud of atoms, an entire cloud starts to behave like a one single quantum entity. You can look at it with your naked eye. You know? On a camera, this is what it looks like. It looks like basically you have a thermal distribution of your clouds. So this is just a random cloud of atoms. And as you cool down, they become denser and denser because they come closer as they get colder. And then you get this very high peak, right? Now, this macroscopic sort of matter wave is is entirely it has a single wave function all over the object, right? So it's a single matter wave. It has a single phase over the entire object, and it's a truly quantum object, right? What that means is that since it's a wave, if I overlap two of these objects, I expect to see interference, right? This is remarkable. This is exactly what you see here, because it almost means as if one atom from one Bose-Einstein condensate and another atom from another Bose-Einstein condensate, when I overlap them, I get zero atoms. That is so counterintuitive. Well, of course, the atom wasn't destroyed. It just appeared somewhere else, but it's so counterintuitive, right? Sorry. So this was first realized in 1995 in MIT and Chilla at Colorado Boulder, right? And it earned Wolfgang Kettle, Carl Wieman, and Eric Cornell the Nobel Prize in 2001. It was a fantastic feat back then. And Wolfgang Kettle, in his Nobel lecture, which I really recommend you to watch, kind of explained this phenomena in the following way. He said that atoms in a thermal cloud, right, like in air around us, are like people at Rajiv Chowk metro station. So he of course didn't say Rajiv Chowk, but it's like people going about randomly. Yeah, no direction, no sort of crosstalk, just randomly going their way. But atoms in a Bose-Einstein condensate are like people marching together in synchrony, right? And this sort of picture was on there on the science cover of Science magazine back in the day, right? So this was all that was happening back in the 90s now, right? It was game changing back then. But I also want to briefly show you the state of the art in ultra cold physics that we are able to do now, right? People are able to realize yet another phase of matter called supersolids. Now, this actually was discovered by my previous group in Stuttgart, by Intelman Faust group. And this object is superfluid, like a Bose-Einstein condensate or liquid helium. It's superfluid and has crystalline structures simultaneously, right? So it breaks a lot of our conceptual understandings of what does it mean to be a solid, what does it mean to be a liquid, and so on, right? Then people are also building these so-called quantum gas microscopes. Here, you put an atom, all your atoms from a BEC, into a lattice, okay, a kind of a grid. Each individual dot here is actually a single atom imaging, right? You can engineer some interactions between your atoms. You can allow them to hop from site to site. You can allow two atoms to sit at one side. There can be an energy associated to it. So you can have lots of dynamics in the system. And then you can start using this system that you can actually image sort of the microscopic details of to model other stuff that we really want to understand, but is really hard for us to sort of see inside, right? For instance, think about magnetism or think about superconductors. We have theories about what's happening with the electrons in a superconductor, but it's very hard to look at those electrons, right? This technique lets us to simulate that and actually look at what the electrons might be doing effectively in this kind of a quantum simulation platform, right? Then atoms also make fantastic qubits, right? You can put them in these little tweezers. We call them optical tweezers, but you can think of them as a chimta made out of light. Okay. So you put them in these tweezers and you just hold them next to each other and construct whatever shape you want. Okay. And then you can make them interact with each other. You can bring them close, you can bring them far, whatever. And each of your atoms is like a qubit, right? A qubit is like a bit which can take 0 and 1 values. A classical computer has these bits. But a qubit, in addition to the 0 and 1 values, can also take any combination of 0 and 1. So it can be somewhere in between 0 and 1, this sort of weird quantum superposition, what we call it, right? So this is a very budding field, right? Then people are also using the matter wave properties of atoms to do interferometry, and you can do very precise measurements of gravity with this technique. Yeah. Then I told you that spectroscopy is very useful for fundamental physics, right? So some of the things that people do now in precision spectroscopy is that in CERN, for instance, there are experiments where they take matter and they take antimatter, so hydrogen and anti-hydrogen, and they do spectroscopy at both of them. Now, the best of our understanding of physics says there should be absolutely no difference in energies between them. They should have exactly the same transitions and spectra, matter and antimatter. But if we can search for a tiny difference in their spectra, that will hint towards a lot of beautiful undiscovered physics, which can be really exciting, right? And then lastly, there's the example of atomic clocks, right? This is arguably some of the most relevant things to you and me, in that we have all used GPSs. It turns out that the satellites that control our GPSs or send us the information and data for our GPSs are in Earth orbit, right? So they are in outer space. They are experiencing a very different gravity of Earth than we do on the surface. Now, Einstein's relativity tells you that time is going to move a little bit differently for the satellite than for us, which means we need to keep very close track of the satellite's clock and our clock. It's so precise, the requirement, that the only way you can do this is with clocks made with atoms and clocks which use the atomic transitions to keep time. So you have atomic clocks on the satellite, atomic clocks on Earth, and we constantly compare their times to know exactly what the time on the satellite is. And this is very important to get precise GPS locations. Yeah. That brings me to the outlook of my talk. We've come a long way. We started from these very simple, basic questions of what are atoms, how big are they, what's inside them, and how do they move, right? And then we went on to beginning to understand how to control them, right? How to make them colder, techniques of laser cooling, and how we can benefit from them, right? And then we sort of touched upon what is a quantum object really, and how to make a quantum object that we can look at with our naked eye. You know? And at the very end, I was able to just briefly tell you something about the frontier research with atoms, right? From quantum computers to a new generation of sensors, new phases of matters. And there's so many more interesting things that we can talk about. But in the interest of time, I will have to leave that. Thank you so much for your attention. That's all from my side. And I just want to thank the organizers again for giving me this opportunity. And Miss Nopani, Miss Pragya Nopani in particular, for inviting me. And for those of you who don't know, Miss Nopani was my high school physics teacher, and I suppose arguably a big reason why I'm a physicist is the classes by Miss Nopani. So I owe a lot of gratitude for that. Okay, thank you very much for your attention. I guess we can take some questions now.
Yeah. So, uh, I can see Karthik has raised hand. Would you like to ask something, Karthik?
Yes, ma'am. Uh, so again, thank you. So my question is, How does zero point energy affect the behavior of Bose-Einstein condensate if the atoms can never uh, truly reach a state of absolute zero or absolute rest, maybe?
So usually you always have a Bose-Einstein fraction and a thermal fraction in your cloud. Like you will, but you're able to reach very high Bose-Einstein fractions, right? Because um, of course, it's going to be a pure BEC at exactly 0 Kelvin, which is not achievable. But at finite temperatures, like the nano-Kelvin temperatures that we can reach, it's almost what 95, 99% Bose-Einstein condensate or something like this, and the rest is just thermal atoms.
Thank you, sir.
So you said something about a single atom being trapped in a laser. You
Yeah.
showed one picture also. So how is that done?
Um. Are you okay? So you have heard about a Zeeman shift, right? I guess Zeeman shifts are discussed in school. So when you put your atom in the presence of a magnetic field, its internal levels can undergo some energy shifts. These are Zeeman shifts. A similar phenomena also happens in the presence of electric fields. It's called Stark shifts, Stark effect, right? So if you have a DC electric field around your atom, the energy levels will change. Okay. It turns out that it's not just a DC electric field that causes a Stark effect. You can also cause it with an AC electric field. Light is an AC electric field, right? So in regions of high intensity of light, the atom will see more energy shift than in regions of low intensity of light. Now, if I have a focus in my laser beam, okay, a laser beam is coming and it has a spatial focus and then it expands again. In the region of the focus, there is going to be a higher energy shift than anywhere else. This forms a kind of a potential well for the atom where it can sit. This is called the dipole force.
So what are the challenges and right now, and what exactly are you trying to uh, achieve now in your research?
So the examples that I showed you are all the things that are happening worldwide, right? My particular research is actually a little bit different that we did not have a time to get into. So I've showed you how laser cooling atoms works, right? And it works very well. People discovered this in the 80s and 90s, and we're very good at it now, right? It's a very sophisticated technology. It turns out that if you were able to do the same thing with molecules, now which are much more complicated objects, they have more structure in them, they have reduced symmetries, okay? So it's much harder to work with molecules. If you could laser cool them, then a lot of even cooler physics applications get unlocked. I essentially work on developing techniques of laser cooling molecules now, of extending all of these techniques from atoms to molecules and figuring out how do we make this work in molecules as efficiently. Once we can do that, once we can cool molecules that efficiently, then we will use them for precision measurements that will tell us something about why is there so much matter in the universe than antimatter, right? It turns out that the best theory of physics that we have right now for particle physics, called the Standard Model, it predicts that there should be equal amounts of matter and equal amounts of antimatter in the world, in the universe. And if we had this equal amounts, then this would just come together and probably sort of annihilate each other, and then you would have a universe full of photons. But there is obviously this observed asymmetry where we have matter everywhere, all of us has matter, but we barely see any antimatter in the universe. We can make it, it exists, it's true, but where is it? Where did it go? Is it that during Big Bang there was an asymmetric amount of it formed? If that is true, then our theory is wrong. And we need to find an addition to this theory. To find that addition, where that addition might be and what it might look like, we have to do these measurements with the molecules.
Amazing. It sounds so unreal, yet you're working on it.
Yeah, functionally, it's just a lab, like I showed you. My colleagues and me in the lab. It's Yeah, it's a lot of lasers, it's a lot of vacuum system, a lot of electronics, cryogenics, and it's very hands-on work most of the time, right? Like you spend some time doing coursework, learning about these abstract concepts, but most of the time as an experimentalist, I work with my hands. I'm screwing screws. I'm thinking about, oh, how do I design something for the mechanical workshop? We have to learn how to design mechanical parts and make proper mechanical drawings like engineering students do, and then give them to the workshops. They make it for us. We have to design electrical circuits. We have to design optical setups. I have to design a vacuum chamber every now and then, right? You have to think about fluid dynamics. How is my vacuum going to be created? How good is the vacuum going to be? How should the geometry of this chamber be to have the best vacuum inside? Things like that.
So, is there any field of physics left out that you don't use?
uh, Astronomy.
Okay. But then you will get there ultimately, isn't it? Because if you're talking about the origin of universe,
Yeah, indeed.
antimatter, so that's not really left out.
Yeah. The thing is that at this stage, the way physics I feel works is that we have such niche disciplines, each of us, right? Like I understand a lot about this field, but I have very little understanding of the rest of physics, right? And so I have a collaborator who maybe does the particle physics side, right? Who knows a lot about how things at CERN work or how all of these particle physics calculations work. I have another collaborator who maybe understands more about let's say laser technology and things like this, right? All of us have to sort of come together and put in our little expertise, and then the whole big result is produced. So I would most likely, I will do some measurement with my molecules, and I will get a number out of it. That number directly does not tell you anything about cosmology or the universe, but that number is going to be given to some high energy theoretical physicists, and they will use it in their calculations to make some sense out of it. So it's a very sort of interdisciplinary collaborative field.
Wow. So you might see something and you wouldn't even know its significance, and you're kind of at the mercy of others to see the significance
Yeah.
in that.
So it's like they have already calculated some sort of ranges that if we measure a number between this range and this range, it
Hmm.
means something cool. Exactly what, we will have to then work it out, but it means something nice. So we know when to be happy and we know when to be sad, but we don't know what we are happy about. Yeah.
Are there any other questions? Other people wanting to ask something?
Yeah, ma'am. Hello, I'm Garima this side.
Yes.
Uh, I just would like to ask one question. Hello, it was really nice. I am a school teacher. So,
Mhm.
if we want to create this interest in the young age about the quantum physics, okay,
Mhm.
how can we introduce children in the class? See, it's not easy to introduce beyond the curriculum in the classroom time within 40 and 60 80 minutes, including all the curriculum. But sometimes some children are very interested in quantum when they hear about that. So how can we introduce that interest during our regular teaching?
I see. Well, I mean,
Just for
pedagogy
me,
is really not.
sometimes just student are, but we ourselves are not the way you have taught and the way you have discussed this was, it was really amazing, beyond our thinking, I think so, being a simple school teacher. Okay.
So what I can certainly say is that there is definitely a lot of interesting content on YouTube right now, right? Like this is a very interesting time, right? Because believe it or not, much of quantum physics that I've learned at least the foundational principles. I did not learn it in my lectures. Of course, we had lectures in university about it, but I would just go to the lecture and like be like, okay, I understand 50% of it. And then there are lecture series on YouTube that you watch. And this is, I think, also what all of my colleagues and everybody does.
Yeah,
And
which
they
one is the see? Because YouTube, if you will hunt in the internet, it is a like a pool, big pool, where what which gives you
so there
relevant
are definitely some
information.
famous professors that have really nice series. Like I think some of the most accessible content for young students is by a person called Leonard Susskind. He's a very famous theoretical physicist, and he has very nice sort of educational videos for first year undergraduate students. And
Could
that's
you
his.
please speak again his name, Leonard?
Could you just
I can.
write the
Yeah,
spelling in
that
the
would be
chat?
great. Yes, thank you so much, Pragya ma'am. That's nice.
Yeah. So Leonard Susskind also has these books called Theoretical Minimum, and they're very nice books, sort of, But of course, this is not an exhaustive list. It just there's of course there's a lot of ideas, and I think beyond that, I would definitely say that while it's very interesting to learn about these new fields of physics that are happening, and I feel like initiatives like Anveshika, where you get to sort of introduce yourself to ideas like this, is very nice and it's very useful. Perhaps, in my understanding, to fully appreciate all of this physics, you kind of the hard truth is that you need to learn the basics properly. And in which case, which is exactly why it's important that we keep the education in school also as strong as it is, right? Like all the basic concepts that we do right now have to be taught still. You can't gloss over those concepts. So it's a marathon. You can't sprint it, right? So, but I don't know. Maybe there is a better answer to this. I am not a
Thank
pedagogical
you so
expert.
much. Thank you so much. Much appreciated. Thank
Okay,
you.
I see some questions from Gopinath and KS Singh. Maybe Gopinath, you start. Okay, now they disappeared. Well, okay, then we can take the question
So
by KS
Gopinath,
Singh.
you wanted to ask something? KS Singh, Mr. KS Singh.
Yes, ma'am. I have raised the question in the chat box also. What I wanted to know is there any limitation of laser cooling? Why we can't achieve 0 degree Kelvin with laser cooling?
Okay, can you still see my screen?
Yes.
Yeah, so okay, so laser cooling, the best we could do was this picture, where we were climbing the hill. Mm, at some point, your atom will be climbing the hill and then scatter a photon when it's at the top. And when it scatters the photon, it still gets this random recoil from the photon, if you remember, right?
Yeah.
That random recoil, that random walk is always going to be there. Because as long as you scatter a photon, you get some random recoil. So the minimum energy you could reach was the single photon recoil limit.
Okay. Okay.
Yes. And the reason you can't reach absolute 0 Kelvin is because that's a theoretical temperature. It's not physical to reach that, right? Because even vacuum of space, even vacuum has energy. And this now touches upon an even bigger sort of Pandora's box of physics, something that comes even beyond quantum physics, which is quantum field theory. This is exactly what particle physics is about. In that, even when there is vacuum, there are sort of fluctuations of virtual particles, right? And I mean, I feel like this is maybe very premature to comment on these things, but basically there is a very small energy associated to nothing. Even just existence in this universe has an energy associated to it, and therefore you can't have 0 Kelvin.
Something sort of a limit imposed by uncertainty principle. Can we interpret like
No, not necessarily. So the uncertainty principle imposes a limit on you measuring two quantities simultaneously.
that?
You can make you could so uncertainty principle does not impose a limit on you fixing one quantity, right?
Yeah.
Like you can measure the position of something absolutely precisely, but then in
Mhm.
exchange you will just have zero information about momentum, but you can
Mhm.
measure the position perfectly exactly.
Or you can
If
say
you
it's something like the vacuum fluctuation energy, something like that, like that
That's
also.
exactly what it is, right? That's exactly what I'm talking about. The fact that there is energy associated to nothing is the vacuum fluctuation energy.
Okay.
And yeah,
Thank you. Okay, thank you.
Any other questions? Uh,
Excuse me. Hi.
yes, Jayati ji.
Hey, good evening, ma'am. My question is, like sir asked ki why we can't get like absolute zero Kelvin temperature, right? Like we say that um I'm also a school teacher, and to students, when we talk about like anything, we wanted to cool something, like you talked about matkas, that even for that cooling effect, that heat, they need latent heat, and that gets from the water that is inside the matka, so that the it can get evaporated. So basically, something we need to cool it down. We are basically removing the energy of that certain object, or if we talk about atom, right? So I'm not sure, am I getting on the correct path or not, but as you talked about that the atom has to climb up that hill, and then it would scatter the photon, and the photon would take away the energy, that potential energy, and then it again has to go to the next one. So then that means there is a limit. uh, 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 that's why, because for that particular atom we cannot take all the, where that kinetic energy is going, like some of that kinetic energy is getting away with the photon when it reaches the maximum potential energy. At what point the kinetic energy would become zero for that particular, like let's say, atom or a electron, that at what point, like every time it climbs up the hill, it is losing some
mhm,
kinetic energy, right?
yeah,
So
yeah.
it like in the figure, the hill is of like same height, right? It that same energy, so it's all the peak at the same energy, or at eventually the peak starts to decline, because part of potential
I
energy.
no, I think I understand what you mean. So the peak is coming from an external field that we have imposed. We have imposed this landscape of energy. Okay, so this is really constant everywhere. But the atom indeed. So let's say the atom started, just to put numbers into it. Let's say the atom started with 10 units of kinetic energy. When it climbed this hill, let's say it lost 1 unit. Okay, and then it that 1 unit was carried away by the photon, and the atom gets transported here. Now it climbs another hill, and it after climbing this second hill, it has only 8 units of energy left, kinetic energy left. Yeah, so it has to go over, let's say, 10 hills, and afterwards, after crossing 10 hills, it has no energy anymore to even climb another hill, so it just stays there at the bottom. It can't climb anymore.
Okay, all right.
That is exactly how it is coming to rest, right? Because
Yeah.
climbing the hill is actually moving in space. As it
Okay.
has to move in space, it climbs the hill. This is precisely where the slowing down is coming from, because it
So
can't go
this
any
is
further.
how we are basically cooling the atoms, or like we
Yeah.
are cooling the matter, right? So that means we can't get like for beta decay also, the graph, it goes like infinity, and it doesn't meet at the x axis. It eventually just go on. There is still a gap. There is no meat over there. So basically, if the hill is going like this, uh, I don't I'm, uh, like eventually the energy will what you are saying, that eventually the atom will not have more energy to climb up. Let's say after 10th hill, that atom does not have any energy to climb the 11th hill, right? So
Yeah.
that's how the cooling is done. Um,
Yes.
right?
Yes.
So that means if we are not getting to zero Kelvin temperatures, that still there is a energy for an atom to climb. Is it so? I'm I'm
Well, it doesn't have enough energy to climb the complete hill, right?
okay.
And
Uh,
it can have still some energy left, right?
right.
And it certainly has the energy that it got from this photon when it when the photon
When
was
it's
emitted.
recoil energy, some.
Yeah, yeah. So it has a little bit of energy, right? Like there are different scales of energy here. So this hill is on the, I think, on the level of maybe tens of microkelvin,
Okay.
and the atom can then still have energy left corresponding to a few microkelvin.
All right. Uh, Thank you so much.
So, Minish, you wanted to ask something?
Yeah, Dr. Garg, it was a pleasure listening to your mesmerizing lecture. I just wanted to have a little understanding that the quantum computers would be able to do much more faster calculations. But at the same time, through your talk, I understand that how early you think we would be able to reach a quantum computing systems, and will it be energy efficient, and in that direction is my question.
I think so. I was at a conference with. First of all, sorry, I'm not a doctor yet. I don't have the title of a doctor. I should mention that I'm still a PhD student. But hopefully soon things go well. But
Yes, yes.
I was at a conference recently, and like I was attending a talk by, essentially, we can argue, like sort of the person of neutral atom quantum computing, who has some of the most advanced systems in their lab. And of course, everybody was asking them the same question. When do you think you're going to have that quantum computer ready? I will just sort of reiterate their answer because I think they're much more qualified to comment on this. And they said, well, it can be next month, or it can be in 20 years from now. We don't know, right? The thing is, when you do something new, you have a plan to get there. And if things work, then you get there in that time. And our time frame for that is about 10 years. The problem is that when you're doing something completely new as a civilization for the first time, you don't know what more problems you're going to land into. So there are sometimes roadblocks that we get stuck on. The roadblock that we are stuck on right now with quantum computing is that there is obviously some imperfections in a computer. And for these imperfections, you have error correction. Okay. So for every logical qubit that you have in your system, you need a certain number of error correcting qubits. Error correction works very well for classical computers, which is why they are so great, right? Error correction is used for all sorts of servers and these kinds of big super computing clusters. They are all error correcting systems. In a quantum computer, you also need error corrections, but it's much harder to achieve this. And as of now, we can achieve it only for very small systems, but it gets exponentially harder for a larger computer with lots of qubits. So the question is that how big of a quantum computer do you want before you call it a quantum computer? We still have quantum simulators, right? Like I showed you these quantum gas microscopes. One can argue that that is still a kind of a quantum computer because you can still simulate a very real physical system on it and discover new physics from it. Yes, but it's not a logical computer with logical qubits in the style of our classical computers. So in that sense, there are certainly like a couple of these challenges of scaling and error correction that remain to be sort of sorted out with quantum computers. And the question is that, okay, we sort of make incremental progress with each of these, and it's difficult to say that at what point you classify that as a full-blown quantum computer, right? Like the truth is that even in their final stage, quantum computers are only going to be useful for a certain class of problems. It's not that you will have better Zoom calls with quantum computers, right? You would have just better quantum chemistry calculations with them. You would have better cryptography, more secure banking, and stuff like that. So there's a very niche class of problems that they will be good for. And for each of these problems, there is a different size of a computer which is going to be required, I think. That's what my understanding is.
Thank you. Thank you very much. That was very well explained. Thank you.
So, Dr. K.S. Singh, do you still have a question?
Yes, ma'am. Not questions. I want some query.
Yes.
Uh, Ma'am, I want to request Mr. Mr. Garg to
Mhm.
share the references he referred to and he mentioned in his talk through you or through some channel of Investiga, so that even if we cannot do such type of works personally, we can instill our students that this sort of works are going on all over the world and in premier institutions in the university. And you can pursue these fields if you want to be a physicist, either as a theoretical physicist or as an experimental physicist. So the problem is where to start is the problem for us, and how to guide our students is also a problem because we don't have resources and we do not have library access. So if we can share the references of the pioneering works and those works which are in much in very much uh, in what do you say uh, people are pursuing these days, then
So
we
what I can
can
actually comment on this,
uh,
uh,
yes, please.
sorry, yeah, what I can definitely say is for bachelor's level students, I think
Yes,
bachelor level students have to do a project in their
yes,
final year or something.
yes.
For them, absolutely. There are labs in India. There are labs in the Raman Research Institute in TIFR in
uh,
Bombay.
uh,
In Then there are theoretical groups in HRI Harish Chandra Institute in Allahabad. There are labs in ISER Bhopal, in IIT Kanpur, I think, in IIT Roorkee that are doing very similar experiments to the kind of things
no,
I'm presenting here.
what I mean is
And
that what I mean is that I'm working in some college which is very interior part of the UP, and the problem is that even if our student wants to go for the project work, then don't know where to go. And you mentioned some places, and I can
mm,
tell you, but uh, what should they tell to the professor of those institutions that I want to do this type of work and I want to pursue such type of career and such type of field? That is what they are lacking. But if they prepare beforehand, before going to those places, that these are the fields people are working all over the world and the people are
mm,
running after these
okay,
fields, then and
okay,
they can get this information if they have some exposure, a superficial exposure of those fields through papers or popular articles. This is what I mean. And because we are not getting proper literature access, we are not able to guide our students.
okay. I understand. I suppose this talk will be available in a recorded format,
Okay.
right? So I think some of my references should be available there.
Yeah. You have covered a lot of references, but uh, other than that, I would like to request you to share references, and it's very short write-ups for popular in the form of popular articles for Indian students, and share in our in group in Vesika website or through Madam Nopani. Then it will be very helpful for us.
Okay,
So
I
what
will share that.
I could request personally would be if you come across any articles which you think are very interesting related to any kind of latest research which people at your places have access to but we don't have, or we don't read those kind of things, we are not even aware of them. So if you happen to read something, maybe you would be kind enough to share on WhatsApp, and then I could probably share with
Sure.
everybody in different groups.
Yes. This is what I want to mean, ma'am.
That if possible, of course, you're so busy, I do not I cannot presume upon your time and your.
Yeah, yeah. So,
No, no,
uh,
of course, I can do
please
that.
don't neglect your work, and we don't want to exert pressure, extra pressure on your work schedule. When you free and you get time, please do a favor for us.
Certainly, certainly, of course.
You you've created so much of interest since been such a wonderful talk, and we've presumed without even asking you, we went on asking questions. We didn't ask you whether you had time or not, but it has been really so interesting. And as I conclude today's webinar, I really, really would like to express my heartfelt gratitude to you, Tatsam, for such a wonderful and thought-provoking session. And the it came straight from heart, and you've really affected us. It's been so beautiful a time that we would like to go on listening. And this gave us really a fascinating glimpse into the world of ultra cold physics and quantum science, and from understanding how atoms interact with light to learning how scientists cool atoms and molecules to extraordinarily low temperatures. The session really beautifully showed how fundamental scientific ideas can lead to extraordinary discoveries and technologies. And you put it so simply that we all could understand complex ideas and processes. And we are really grateful, deeply grateful to you for taking time out to share your knowledge, experience, and insights with us. Your presentation combined a rare depth, clarity, enthusiasm, and you made the session intellectually enriching as well as deeply engaging. So thank you so much for that. And I would also like to thank all the participants for joining us and for being such an wonderful audience. Um, and your questions are what made the session all the more meaningful and engaging. And we hope that today's session inspires you to continue exploring the fascinating world of science and to actively participate in NEST 2026. I would also like to express my heartfelt appreciation to all the organizers and Vishika coordinators, the technical team members, and volunteers whose continuous efforts make this webinar series possible. And a special note of gratitude to Professor Verma, uh, former professor at IIT Kanpur, for his constant encouragement, guidance, and inspiration to this initiative. Thank you once again for to everyone for being with us today, and we look forward to meeting you again in the upcoming session of NEST 26 webinar series. Have a wonderful evening ahead. Thank you so much.
Thank you, madam. Thank you.
Thank you very much for your kind words. Yeah, it was a pleasure
Pleasure.
giving this talk,
A
and
pleasure.
yeah, yes, and I'm always happy to sort of get in touch and I don't know help with any sort of ideas or guiding students if they are searching for masters, PhD positions, and so on.
Okay. Thank you so much. So, oh yes, there's another hand. Can I presume upon your
Hmm.
time more?
Yeah, sure. Yeah, sure. Yeah.
Yes, sure. Yeah. Shaurya, want to ask something, or is it by mistake that you raised your hand?
Hello, good evening, sir. Good evening, ma'am. I actually wanted to thank you for taking out the time and produce such a meaningful information and sharing with us about the quantum physics and these topics. I look forward to learn more from you. Thank you so much, ma'am.
Thank you very much.
So maybe we could have another webinar from Tatsam if he has time and uh, if he can come back to be with us again. So,
This is the thing that I know about, so it would be a repetition of this. Or if I talk about more advanced research, I feel like that is more of a graduate level thing where I can talk about my actual research and like sort of more cutting edge things. But at a school level, I feel this is
yeah,
where my
maybe you could
expertise.
tell us what kind of problem you faced, a specific problem, and how it was solved through collaboration, specific examples, and uh, maybe we'll not understand too much of technicality, but maybe some kind of a simpler idea of the problem at hand, and then how it was solved, because that aspect of science and research is hidden from everyone. Because here research mostly involves, I'm not really competent to answer that, but what I get to hear is people read a lot of things and put things together, but the kind of research that you are talking about is a cutting edge research where you're doing something for the first time maybe, so there are a lot of bottlenecks and uh, about which you really have no idea probably how to go about it, and then you talk to different people and somebody suggests something, or you get an inspiration or something clicks and then you try it out. It's like groping in the dark probably sometimes. I don't even know whether I'm able to express myself, and whether it is possible even for you to simplify that, or how you are doing some problem solving. It's just a
I
thought.
think so. It's a very good question, because I have to say this, I guess, and you can relay this to your sort of school students, that people often have this understanding, and I did too, that in my college and like university, masters, and so on, I'm going to learn about physics. Truth is, of course, I learned some physics, but like I forget that. I learn something and I forget it the next week. I have a terrible memory. You don't go to college or whatever to learn physics. Actually, you learn just a way of thinking. You just learn how to solve a problem. In physics we call some this, consider a spherical cow. Okay, so we have any problem, we break it down to the simplest, most ridiculous approximation. Okay, you have a cow and you want to understand something about it, you call it spherical and then think about the problem, because we are working with spherical symmetries. Right? So this is sort of the approach that you learn, right? Like, okay, every time you're like, I don't know what to do now, you just zoom out, strip away everything which is complicated, and just solve what you think you can solve, and then add one element after another, kind of. This is the sort of style of thinking that is ingrained in you in all these years of college and university
Yeah,
life.
so exactly this one. Can you sort of, you know, take us through that tunnel where you had a big problem and then you stripped it and then you found a small way, and then again you found a blockade, and then you stripped away everything and then you made a small place. Uh, I mean,
Okay, allow me to ideate for some time and I
yes,
will see
exactly.
if
Please
it's
take your
possible.
time, and you may not even have that much time for us. I understand. It's just the way so beautifully you told us everything, we got extra excited. So just ignore that excitement and see if you ever get time. We'll be grateful. Thank you so
Absolutely.
much. It
Thank
was
you.
wonderful to have you.
Likewise. Ciao.
Ciao.
Okay, bye everyone.
Bye. Bye. So we'll close it now.